I want to introduce our technology for advanced LiDAR sensors for passive and active imaging applications. Our company is located here in the south of Germany. Currently, we have approximately 410 employees. Revenue last year with more than 90 million euros. We have two shareholders, Dean and Rheinmetall, sharing 50%, and we have more than 2,000 square meters clean room facility to produce these detectors. So our core business is really producing the infrared detectors based on vacuum cadmium telluride. We got a lot of developments funded by the German MOD, so it's a national key technology. And we are working on the next generation of infrared detector modules. So we are starting really with chemical elements. First, we grow our own substrates for producing the detectors. Either we use liquid phase epitaxy or molecular beam epitaxy to grow the detectors. So by the mixture of cadmium and mercury, we tune the cutoff wavelength of the detector material. And by the epitaxial growth, we get the detectors sensitive in the right spectral range. What's also important, of course, is the readout technology made in silicon. Currently, for most of our readout circuits, we use 180 nanometer technology. In principle, it's converting the photocurrent into a voltage, and then the silicon readout chip provides the readout. We have also the other technologies in-house, like packaging, cryogenic packaging, to operate the detectors at the desired low temperatures, something between 60 and 180 Kelvin, depending on the detector material, detector spectral range, and so on. We have in-house also fabrication of cryocoolers, which we use for our detectors, but also we use in some cases Joule-Thomson coolers or rotary coolers, which we source from external providers. And the core product is then really the integrated detector cooler assembly with the detector chip integrated in the DUR, in the vacuum, then the cooler to operate the detector at the desired temperature, and then proximity electronics operating the chip. And this is our core product of our company. So we are using vacuum cadmium telluride. With the material system, we can tune detectors sensitive from shortwave to very long wave. We work on high resolution detectors, realized by small pixel pitch, but also implementing low size weighted power by our high operating temperature technology. By measures, we increase the operating temperatures of the detector so that we can either use smaller coolers or achieve faster cool down times. And we are working on dual color, dual band technology, providing two or more spectral bands in 1 pixel. And I just want to show you some of those state-of-the-art products and our future trends. As I said, we cover shortwave from shortwave up to very long wave. We concentrate on extended shortwave, which provides also some content in thermal radiation. Of course, typically in the applications, you have different conditions and tasks, atmospheric conditions. You operate at day, at night, sunshine, fog, haze, rain, snow, turbulence. So this is the atmospheric condition. You have different objects you're interested in, tanks, vehicles, UAVs, missiles, persons. And you have, of course, also these different tasks like detection, recognition, identification. For our standard mid-wave or long-wave sensors, high resolution and low swap, we work with LPE-grown MCT on latest matched cadmium telluride substrates. So for the mid-wave spectral range, typically 3.4 to 5 micron, we operate these detectors nowadays at 120 Kelvin using our P1N technology. We have in parallel a hot technology available, operated at 160 Kelvin, which is used for low swap applications. And for our long wave modules, the typical spectral range is 7.6 by 9 micron cutoff wavelength. There, for the latest products, we're also using PON technology, allowing us an operating temperature of 100 Kelvin. And so finally, by reducing the pixel pitch, we come to large format arrays. For example, our 1280-720, the 12 micron pitch, frame rate up to 75 Hertz, or an XGA format, 1024 by 768 in a 10 micron pixel pitch, and the 1280, 1024 by 7.5 micron pixel pitch. This is currently our smallest pixel pitch. Depending on the size of the focal plane array, we need different DUA technology, and we can configure the complete detector module by choosing the right type of cooler for those detector modules. However, one issue for the small pixel pitch is the available charge handling capacity and your achievable any delta T, your thermal resolution. We are somehow limited by the small pixel sizes. Currently, with this 180 nanometer technology, CMOS technology we are using, we achieve approximately 2.1 million electrons. This gives you an any delta T of approximately 30 millikelvin, operating this detector at half Welfare condition. Depending on your application, we have here some examples showing the difference. For example, the characteristics of the object is different. You see here this very nice images with a rotating blade of the helicopter. For the long wave detector, you have most of the photons. You have very small integration times, good for fast moving objects. With longer integration times, you get the blurring of the image, or of course, often you are limited by your background. Comparison, for example, between midwave and long wave, much more gladder by sunlight and reflections in the midwave than compared to the long wave in that type of scene. The future trend is really to go to a full HD format. So we are working currently on a 5 micron pixel pitch to be realized in the upcoming years. Another topic is being sensitive in more than one spectral range. We work here on our dual color, shortwave, midwave, or midwave detector technology. Currently, we have a detector architecture available, allowing spatial and temporal coincident registration of the signal. This is fabricated with our NPE-grown MCT on gallium arsenide substrates. It's a 320 by 256 with a 13 micron pixel pitch. The spatial coincidence is achieved by a symmetrical and concentric areas for both photodiodes. And we have 2 contacts per pixel, so we can read out both photocurrents at the same time. We use for this type of detector our MCT NMP array technology. And we have a dedicated readout circuit, which has a direct injection input stage. We have 2 gain stages with different charge handling capacities for the 2 colors. We have snapshot integration, and we can operate the detector module in the single color, dual color, or HDR operating modes. And depending on the integration time, we can achieve a frame rate up to 500 frames per second. We have realized this technology in shortwave midwave. This is the upper image, or in midwave, which is then typically used in missile approach warning systems. Currently, we are working for this technology on a pixel pitch reduction so that we can also achieve larger formats with this type of technology. And finally, like the presentation before, we also do work in the shortwave spectral range. We concentrate on detectors with a cutoff wavelength of 2.5 micron. Typical applications are hyperspectral imaging, low light level imaging, or even active imaging by laser illumination. So typically the spectral range is 0.9 to 2.5 micron. We have a visible option by removing the substrate. where we grow the detectors. Then we can go down to 0.4 micron for the cutoff wavelength. The typical operating temperature is something between 150 and 175 Kelvin. And those type of detectors are cooled by a Stirling cooler. We have large format arrays for push-boom imaging, for example, in airborne applications like 1024 by 256, going down to very small pixel pitches like a 640 by 512, which comes then also with low size wake and power requirements. The typical frame rates go from 250 to 100 hertz. You see some examples of the imaging. Since we have with the 2.5 micron spectral range also a part of thermal radiation, you clearly see a thermal image when you have no light at all during night condition. However, when you operate the same sensor under day condition, then you are mainly driven by the reflective image. We have also some examples in fog condition comparing e-sphere with visible camera, and also the effect of active illumination in nighttime. When you operate the sensor without illumination, you have the thermal image, and you can use a laser for active illumination, and then you get a reflective image instead of a dominated thermal image. So these are 3 examples of our current technology. For our extended shortwave detectors, we work on higher frame rates by also having a higher resolution of the detector. And this is just an overview of our current technology.